Okay, let's take a look at example 2, distinct linear factors. We'll move a little bit faster this time when it comes to determining the actual coefficients themselves, since we saw in the previous video, in the previous example, these two methods for determining the coefficients. This one will be faster. So here, just to double check, we've got a rational expression, check, and it's proper because the degree in the top is 2 and in the bottom it's 3. So we've got a higher degree in the bottom, so it is proper. It's important that you verify that because partial fractions doesn't work, at least not immediately, with improper fractions. You first have to do some long division or another algebraic trick to split it into a couple pieces, many of which are proper, and then you can run partial fractions on those proper fractions that you get. We'll cover that in a specific example later on. But for now, we got proper, so it works out. So what we're going to do here is factor the denominator. So we've got the numerator, x squared plus 2x minus 1. And then if we factor the denominator, we'll take out an x, and then we'll have x squared minus 1. And then this further factors, actually, into x plus 1, x minus 1. And now I can't remember if I said that this was repeated linear factors. We're doing another example of distinct, so I just don't remember what I said. Okay, so now we have the denominator fully factored into either distinct linear factors or irreducible quadratics. Here we've got 3 different factors, so they are all linear, so they are distinct linear factors. So we already know how to handle the partial fractions decomposition, at least the general form of it. We will put an arbitrary, yet to be determined coefficient over each distinct factor. We'll then multiply by the entire denominator, which will clear the fraction. So the left-hand side, we just get the numerator because the denominators cancel out. And then here, what's in common will cancel out. So here, we're going to multiply by x, x plus 1, x minus 1. The x's are in common, so they'll go away. But here we'll be left over with a times these two pieces, x plus 1, x minus 1. So this will be a, x plus 1, x minus 1, plus b, the commonality will cancel, so we'll be left over with x times x minus 1. And similarly, the commonality canceling, will be left with cx times x plus 1. To figure out our nice values here, we can just plug in the nice values of x. So if x is 0, this would give us negative 1 on the left-hand side. When x is 0, the b and c terms cancel, but we're left with this first term, which would be a times negative 1. So negative a. Well, that implies that a is positive 1. Now let's plug in negative 1. When we plug in negative 1, the left-hand side will actually become, let's see, negative 1 squared is 1, minus 2, minus 1. So the 1's cancel, and we're left with a negative 2. So negative 2. And then what cancels on the right? When x is negative 1, the a term will cancel, and so will the c term. So we'll be left over with the b term, which will be, let's see, this will be negative 1 times negative 2, so positive 2. So 2 times b. Which will give us b equals 1. Sorry, negative 1. Excuse me, negative 1. And lastly, when x is positive 1, the right-hand side of the equation will be 1 plus 2 minus 1. So positive 2. And then the terms that have an x minus 1 will cancel, so we'll be left over with the c term. And if we plug in 1, we're going to have 1 times 2 times c. So 2c. So c is equal to 1. All right. Okay. So if we go ahead and integrate, if we go to integrate this now, this integral here, after running partial fractions on it, would be the integral of 1 over x dx minus the integral of 1 over x plus 1 dx plus the integral of 1 over x minus 1 dx. So this is natural log absolute x minus natural log absolute x plus 1 plus natural log absolute x minus 1, excuse me, plus c. Then, if we go ahead and combine them, not that we have to, but it looks nice, this would be x times x minus 1 all over x plus 1 plus c.